Hello, in this video we'll be looking into the intermolecular force of attraction, that is London force. London forces are also called instantaneous dipole, induced dipole interaction, or dispersion forces, or van der Waals forces. So let's take a look at this particular force. But before we do that, what do we mean by intermolecular? Is there something called intramolecular anyway? So let's take a look at those particular terms. So what is the difference here? Now, we've got the word molecule. What do we mean by the word molecule? So molecule is anything that's got a covalent bond. So we're only focusing on covalent compounds. We're not looking into ionic compounds at all. So when we talk about intermolecular forces, it's all about covalent compounds. Intramolecular means anything existing within that molecule. So if I've got water, I would look into, so water is HOH. What is this bond inside the molecule? So those bonds are quite strong, covalent bond. It exists within the molecule, and because of this bond, the molecule's chemical properties are decided. So that's your intramolecular force of attraction. Let's take a look at intermolecular. Intermolecular, like intercontinental flights, is something that's occurring between molecules. So if I've got one water molecule here and another water molecule here, is there anything occurring between the two molecules? And if there is a force of attraction existing between the two, that's called intermolecular. And when we talk about intermolecular in comparison to intramolecular, they are relatively weak. And the influence of these intermolecular is on the physical properties. So based on the physical properties, based on these intermolecular forces, the physical properties would vary. Now, there are three main types of intermolecular forces. We will be only focusing on London forces in this video. If you're interested to find out about the other two intermolecular forces, then please do refer to the other videos on my channel. But today we're only going to look in this video on London forces. So London forces, as we said, has got many different names. So you can choose what you want to call them by, but do refer to your exam board, because some exam boards would consider van der Waals as a name for nearly all intermolecular forces. So London forces will occur between all molecular forces and separate atoms. Separate atoms say that's for noble gases only. Now, how do London forces occur? So we know that electrons revolve around the molecule. So if I have got a noble gas atom, so this is, imagine this is a noble gas atom, around the nucleus you've got electrons going around it. So that if this is one atom, because the electrons are in constant motion, now imagine this is a table in the middle of the room and people are running around the room. So if that's the table, so that's the table, and people are running around the room. So your teacher says you have to do a loop around the room. So imagine, or around a track in the field. If people are running at any time, at any instant, you will see that some people are clumped up together and there is a lot of gap on the other side. The same thing happens in electrons. Electrons are like people. When they run around the nucleus, they're not always evenly distributed. At any one point, you might have more electrons on one end and less electrons on the other end. So what would happen is there is an unsymmetrical distribution of electron, and that is occurring at any instant. So that's the key word here. And because of that, one end of the molecule becomes partially negative as compared to the other end. So very interestingly, something that was a neutral atom has suddenly acquired two ends of a pole. So it is now a polar atom. It's got a dipole. Now, if that's the dipole there, now what is the implication of that on the neighboring atom? So if you've got a neighboring atom here, that also had electrons revolving around it, but because you've got more electron density here, that's going to repel the electrons on the neighboring atom, and therefore this side pushes the electrons away. So you've got more electrons on the other end and less electrons on this end. Therefore, the first atom has now induced, it has induced a dipole on the other end of that molecule or the atom in the neighborhood. So this is now an induced dipole. Now, we know that there is always an electrostatic force of attraction between the positive and negative. And suddenly, you've got that happening between the two atoms. And this weak force of attraction is your London force. So that is the meaning of the London force or van der Waals forces of attraction. And if you think these electrons are still running around, that means the dipole is going to be destroyed. The instantaneous dipole will be destroyed, and therefore the induced dipole is gone, and therefore the London force is gone. Therefore, this force is very, very weak. It keeps forming and it keeps breaking. Therefore, overall, the force of attraction is extremely weak. The factors on which the London forces depend is the number of electrons and the branching. So let's take a look at both first. The number of electrons, greater the number of electrons, more is the van der Waals force. And you can compare it to people running around the field. If you had 3 people running or 10 people running, you're not going to get more crowd on one end. But imagine 100 people running, and suddenly you've got lots of people on one end and less on another. The same thing occurs with electrons. If you've got lots of electrons on one end, the chances, you've got a greater chance of a dipole to occur, and also the dipole form would be stronger. Therefore, the London force would be strong. More energy is needed to break them, and therefore the boiling point will be high. And let's look at some examples whereby we can see this change. Look at the noble gases, helium, neon, argon, krypton, xenon. As you go down the periodic table, they are changing because the number of electrons are different, and the change in boiling point, you can see the boiling point is increasing. So increase in boiling point, you've got increase in number of electrons, and therefore we know that the van der Waals forces or the London forces are stronger. Same in halogens. As you go down the grid, fluorine, chlorine, bromine, iodine, you can see that the melting point and the boiling point is increasing because the number of electrons has increased. The van der Waals force or the London force is stronger. You can also see the color is intensifying. You can see that the physical state is changing. It's so strong by the time it reaches iodine, the intermolecular forces are so strong that it is a solid. But remember, the van der Waals force or the London force is a weak force. So if you heat iodine, iodine is a black solid, but when you heat it, iodine would change from solid straight into iodine gas, because you don't need a lot of energy to convert or to break that force of attraction. So to convert iodine into gas, it's very straightforward. In fact, it is so straightforward and so quick that it just changes. It skips going from solid to liquid and then liquid to gas. It actually skips that and it turns straight from solid into gas. And it's a beautiful experiment. And that's your sublimation, whereby the black solid turns directly into a purple colored gas. And if you leave it, if you've heated it in a container, let's say you've put your iodine solid here, you could just put a funnel on the top and you will see that this was black solid and the whole thing gets covered in purple gas. And if you see at the top of the funnel, or if you've got a watch glass, you will again see black solid. So the process is solid to gas and gas to solid, and all because it's got very weak intermolecular forces of attraction. Another example, alkanes. Alkanes, as you go down the homologous series, they've got more carbon atoms, greater the number of electrons, therefore London forces increase, and therefore their boiling point would also increase. Branching. If the molecule has got more branching, less surfaces in contact, therefore it will have weaker London forces. So take a look at this. You've got long chain pentane. So if I bring another pentane molecule close to this, another pentane, and then these are all nicely stacked, the intermolecular force of attraction is stronger because there's more points of contact, more surfaces exposed to each other, therefore the intermolecular forces is strong. Whereas in this case, the intermolecular force would be weak because the surface in contact is less. Therefore, branched alkanes, the boiling point would go down as the branching increases. So overall, what we've looked into is that London forces is a very weak intermolecular force of attraction. It's the force of attraction between the instantaneous dipole formed in one molecule or induces the dipole on the neighboring molecule or atom, and it's the force of attraction between these two dipoles that is the London force. London force changes with the number of electrons, so greater the number of electrons, more is the instantaneous dipole induced dipole attraction, greater the branching, weaker is the van der Waals or London forces. So thank you for listening and watching this video. Do like this video if you've understood the concept, and don't forget to subscribe to the channel. So thank you for watching and all the best. Bye.